Welcome back to session 2 today. A quick announcement about our PENC social this afternoon. The location has changed. It will now be held at the Terracon office, which is 2401 Brentwood Road, Suite 107. I will send an email out to those that RSVP'd for the social. Just wanted to give you a heads up about that. Our speakers today are Danny Brinkley, PE, and Benjamin Davis. Danny Brinkley graduated with a master's degree in material science and engineering with a minor in mechanical engineering from North Carolina State University in 1986. He is a member and local chapter officer of ASM International, a member of the Minerals, Metals, and Materials Society of AIME, a member of the National Society of Professional Engineers, and a member of the Institute of Electrical and Electronics Engineers. Mr. Brinkley holds a professional engineering license in North Carolina and has over 20 years of experience in engineering investigations related to material and mechanical failures, problems, and electrical device failures. He has extensive materials characterization experience involving SEM, EDS, XRD, XRF, FTIR, and other analytical techniques. Mr. Brinkley started his career with CP&L in their metallurgical laboratory and remained in this position until Duke Energy closed this lab due to cost reductions. He is currently a staff engineer with accident reconstruction analysis in Raleigh, North Carolina. Ben Davis has a bachelor's degree in biological sciences from NC State. He started working at ARA since 2018, and he runs the CT there. Danny and Ben, thanks so much for being with us. I'll turn it over to you.
All right, thank you.
Thanks for having us.
So good morning. We're going to give a presentation on the use of computed tomography in the evaluation of failed or damaged components. So computed tomography, or CT scans, is an imaging technique that generates a three-dimensional volumetric image of a sample. So as the sample rotates, the CT system collects hundreds to thousands of radiographic projections, slices, that can be later used to reconstruct the 3D volume of the sample. To perform a 3D reconstruction, CT systems require a computing procedure to calculate, locate, and display the point-by-point relative attenuation of the energy beam passing through the sample. So a key consideration to this is that you need significant computing power to do the reconstruction. So some of the limitations of this technique is that the X-ray source, or the X-ray tube, has a maximum power rating that is a function of its voltage and current rating. The X-ray tube and current can be adjusted to tune the system for the sample of interest. For optimal imaging, the system is tuned to maximize the signal being obtained from the specimen. Under proper setup, a resolution of about 1 micron can be obtained. The maximum voltage that we can operate our CT instrument at is 225,000 volts. This voltage level can penetrate about 1 inch of steel, several inches of aluminum, but won't penetrate a 1/4 inch of lead. So the manufacturer of our instrument actually makes instruments that have tubes that are rated up to 9 million volts. So bear in mind that this instrument having that amount of power is the size of a small building. So computed tomography was initially developed in the 70s, primarily for diagnostic medical applications. So it was originally referred to as computed or computerized axial tomography, or CAT scans. So 2 people involved with the development of the CT instruments received the 1979 Nobel Prize in Physiology or Medicine, and that was Alan Cormack and Godfrey Hounsfield. Computed tomography can be used for various types of radiation, various types of radiation can be used to inspect components. However, X-rays are the most common form of radiation used for industrial applications. And I suppose based on the medical applications, people in industry saw that this could be a useful inspection technique, so it was quickly adopted for industrial applications. So we've got a schematic here showing like the main components of a CT system. So you can see the specimen in the center, which is on a turntable, and you've got an X-ray source to the left of that, an imaging plate that projects the image of the specimen onto the sensor, and then a PC for processing all of this. Then in the bottom right, you can actually see a schematic of basically what one of these systems looks like. So you have motorized controls to move the specimen left, right, front, back, up and down, and then rotate it, and the similar controls for the detector array, which is at the left, and also for the X-ray source. So just for, I guess, fun, here's a photograph of a CT system from the 1980s. So this system basically would occupy the better part of a room. So again, the computing power, you think probably we have as much computing power in our cell phones now as what they had in that system in the 1980s. And come forward to the present, this is basically the system that we have at Accident Reconstruction Analysis. So again, this instrument is not small, so you can see the imaging console at the center here of the top left photograph, computer to the left of that, and then at the bottom right, you can see again the sample chamber, and then the console to the right, which is the power and cooling supply for the X-ray tube.
So the high voltage generator and stuff is contained within that cabinet. All of the components for obtaining all of the imagery are within the main cabinet there. So you've got the, I think if we move to the next slide, yeah, you've got the detector here on the left. You rotate your specimen on a stage between your X-ray source and your detector, projecting, through your specimen onto the detector and gathering data that way.
So again, you can increase or decrease the magnification from the position of the specimen with respect to the X-ray tube and the imaging panel. So the CT instrument can be used for accurate, non-destructive measurements of components instead of using a dedicated coordinate measurement machine. The obtained CT data can be used to create a point cloud and mesh for computer-controlled fabrication techniques. CT data can be used directly with finite element systems. The image at the left shows like a carburetor being scanned. So we go forward to the next slide. The results for the CT scan of a carburetor shown in the previous slide. A surface model is shown at the left, and a reconstructed 3D image with different components highlighting as the right image. So note the material will have different densities and can be easily separated in the image. So you can see several different components internally in that carburetor that can be separated based on their density in the X-ray beam.
Yes, this is a good example of how you can take a solid component, extract a 3D model from the CT, and you can use that mesh to, for FEA, or, we've 3D printed some of these. In fact, this component specifically for, exhibits or just for fun. You can isolate out some of those internal components in there if you wanted to model those or measure any dimensions off of those.
So first example here is like a PVC wastewater piping assembly. So this component was about 4 feet in length. It was discovered to be leaking shortly after its installation. It's a relatively low pressure application. It's only about 100 psig. And in this case, the client indicated we could not perform any destructive analysis on this component. So you can see the crack in this T was marked in an arrow in the previous slide, and then a higher magnification of the crack here. So we've created basically a volume of the larger T in that assembly, shown on the left. The crack is marked with an arrow. And then at the right, you can see that same image rotated and translated, showing a slice through the joint between the pipe connecting the two T's and the two T's. So that's
So the CT here allows us to create a section, we'll be able to create a section plane here that you can see in the right, and we can move that, translate that plane along any of the axes, and it allows us to view any internal features, which you'll see here on the next slide. So this is that same plane from the previous slide here on the left, viewed just in 2D. So you're just looking at a single slice of the object. And highlighted by the arrows, you can see some of the internal voids that we detected.
So the key point here is we confirmed the T's consisted of PVC, and you can see the density of the PVC in the lighter area, but you can also see the cement used to join the pipe on the ID to the hub of the T on the OD. And you can see that the cement is a lower density than the PVC pipe. But you can also see these axial radial features in this image marked with arrows that show voids in the T hub. And then another axial slice shown at the right. Basically, the yellow arrow is basically centered on the same area shown in the yellow arrow on the left image. And you can see the apparent porosity in that connection. The other interesting thing to point out here is the difference in wall thickness of the hub on the right and on the left. Okay, so another view, this is closer to the horizontal member joining the T. So you can see part of that at the upper left corner of this image, but we're away from where the pipe is inserted into the T. And you can see these notches along the inner diameter surface, and the crack that was present on the outer diameter is marked with an arrow at the bottom of that cross section. So again, that crack appears to initiate out of a notch on the inner diameter of the T. And again, a higher magnification shot of the cross-sectional slice shown in the previous picture that shows, again, the crack penetrating the through wall, and you can see it faintly at the bottom of that image. Next example is a broken handlebar assembly. So this is an injection molded plastic component, has various types of reinforcement that fractured in service. And again, we were not permitted to perform any destructive analyses on this. But again, you can see like the steering column at the bottom, we've separated the two in the right image to show where the fracture occurred between these components. Here's higher magnification photographs of the broken handlebar assemblies. So again, you can see the reinforcements along the steering column. And again, the fracture of that component is not completely perpendicular, but follows a different angle along the surface. So we CT'd this.
The lower section of the handlebar there.
Yeah.
So on the left here, you'll see the full volume. And on the right, we've got two circular cross sections. So imagine this like, it's almost like a world map where you've taken a circular section and unrolled it. So Danny here has marked areas of interest with 1, 2, and 3, so you can visualize where those are on the scan.
So the key points on these slices are, you can see voids in the top right image in the injected molded component. And then in the bottom right image, you can actually see a void marked with an arrow. And again, you can see the orientation of the fracture surface features kind of pointing back towards the number 1. And again, notice that the component shown in the bottom right image is modeled in appearance. So this is showing the glass reinforcement fibers in the injected molded plastic component. So those features also give you some information about the directionality of the fracture as well. So the
image on the left here is a surface model of that fracture. We found that some of these surface, especially in plastic components, the surface models do a very good job of highlighting features on the surface.
Yep. So as a material science metallurgist, we often look at metal fractures. Plastic fractures are a little different, but these images show the amount of detail that you can get on a plastic fracture surface compared to that of the one shown at the bottom right. So that image at the bottom right is a scanning electron microscope image of a different plastic component that shows really not much detail at all. I mean, there's some features there, but again, nothing compared to what we can see in this reconstructed surface model of the steering column. So the key point here, much more detail in that fracture, and you can rotate it around and view it at various orientations, which it's much quicker than looking at it in an electron microscope. So again, higher magnification images of that surface model. So again, we're using the same numerical designation of the locations on the fracture. And again, you can see the detail that you have in that fracture surface. Again, the features point back to one, suggesting that one was the initiation of the fracture and it propagated from there. On the top right, you can see the secondary cracks off of the primary fracture, which also give you information on the direction of fracture propagation. So the surface model was used, as been said previously, to recreate like a 3D model. So the image on the left shows like a 3D printed replica of the actual steering column fracture, about 3 to 4 times the size of the original fracture, which is shown on the right. So again, if you're going to court to make a point with a jury, again, this is a nice visual aid.
Here's an example of small pins from an electrical connector, both compressed and decompressed. In these, we were mostly looking for solder penetration. They're pressed through a circuit board, and the client wanted to know if the solder was adequately penetrating the through holes.
So the couple of things to point out on this: the overall length of these pins is about 6 millimeters. The diameter of the internal spring is about 1/10 of a millimeter. And initially the client had suspected, so there was issues with electrical continuity on these, so they had suspected that the springs might have failed internally on these electrical switches or connections. And again, as Ben points out, these are through-hole components, and it shows a lack of solder penetration into the through-hole connection. The final point to make on this is that the client determined that these pins are actually supposed to be surface mounting components rather than through-hole components. So again, we don't know the corrective actions taken, but again, these images which were shared with the client remotely allowed them to understand better what was going on with these pins and why they possibly were failing.
And this is a good example of the level of detail you could expect from, a small mechanical component like this. You can see how much detail you have on the spring, given that it's quite small. Okay, so here's an example of a pretty new technology in CT. This is what we call a 4D CT scan. So this is another electrical connector, and we've performed a series of very short CT scans with the connector, moving this jig that I've created in a step motion, so we can create a video of CT scans. So this gives you like an unprecedented view into like a cross-sectional view of this electrical connector in use.
So all of the dark components on this are metallic, and the lighter gray scale components are plastic. So again, you can see the basic operation as this switch is connected, how the various components inside it work.
Yeah, there was some question about how these components interact in a real world scenario, which you just can't get. This is a view you wouldn't, I mean, maybe through sectioning the switch, but then you would damage, or not the switch, the connector, you would damage the components. So this allows you to get a view through these components without altering them in any way.
So the next slide shows a plumbing fixture nut. And again, we don't have any photographs of this component in the presentation, but you can see that there are some marks on the surface of this component to indicate that pliers had been used to either tighten or loosen it, which basically the manufacturer's instructions indicate that this should all be tightened by hand, and there shouldn't be no tools used on it to prevent, I guess, damage to the fitting.
This is also a good example of showing voids within a component. You can see along all of the ridges on this, there's a void associated with most of them.
And then the next slide, go ahead. Whoa, back one. So you want to comment on this one?
Yeah, so there was some question about whether or not tools have been used to tighten or loosen this component. And so we just did a simple section through this nut, and you can kind of see the displaced material to the right side of the indentations created by the tool, indicating that it was likely used to tighten instead of loosen the nut.
Yep. So again, all done non-destructively. So the next component is a under frequency relay. So I've blacked out some of the manufacturer's identification, but again, a client sent this in to us. This had been recently installed and experienced a failure. The troubleshooting at the facility this was used at determined that there was a coil open on the induction cylinder, which is marked with a yellow arrow in the right image. So again, it's a lot of components there, but we'll get into the details of this in the following slides. So the first image here shows like the coil for the induction cylinder with the iron core still present. So again, you've got 4 individual coil windings onto like this iron core to use to create the magnetic field to displace the induction cylinder. So as the induction cylinder rotates, you open and close the switches shown in the previous slide. But again, the point here, this shows one of the limitations of the instrument in that iron core is more dense and interferes with the imaging of the coils in the shot. But again, a lack of detail. And then if we go to the next slide, this is the coil in question on the left with the core still present, and then showing the core after we have, or the coil after we have removed the core. So again, note the difference in the resolution on the magnet wire on the 2 images. So again, this was not completely non-destructive because we had to remove the core, but it did allow us, by removing the core, to image the details of the coil windings much better. So you can see the terminal lead wires coming in here, then being attached to the magnet wire spliced areas. So the OD attachment is on the right in the bottom right image, and the ID attachment splice is on the left. So here's a more magnified image of the magnet wire coming from the ID. And if you look at the image at the bottom right, which is magnified from the one at the top left.
And sectioned along the the failure that we found.
Right. You can see there's an actual break in the magnet wire from the ID. And then you can see that magnet wire is doubled back on itself. And then there's a notch adjacent to the break in the magnet wire. Here's the actual coil. So we wanted to disassemble this actually destructively to determine more information about the failure. So again, you can see the two splice areas on the bottom left and the right images showing like the magnet wire, which is copper colored, and then the lead wire that goes to the electrical connections being tinned in a silver in color.
And the top left image is as it was in the CT scanner. So you can see none of those wires would actually be visible without disassembly of this actual component. So that's why we use the CT to identify the failure on this.
So we began taking apart. So actually the failure was beneath the plastic bobbin. So we had to cut and remove portions of that bobbin to actually access the failure location, which is shown at the bottom right. So again, you don't make out a lot of details, but the actual break in the magnet wire is marked with the black arrow. And it appears to be embedded in some sort of varnish or resin. So it's not like it was exposed and could have been damaged during handling.
So this would be a manufacturing defect then.
Yep. So we cut out the wire. We actually examined the wire failure in a scanning electron microscope. So the top left image, you can see like about half of the cross section appears to be associated with a cut. And then the features shown in the bottom right image marked with a black arrow have rounded edges, which suggests that electrical arcing occurred on this fracture, and shows basically the magnet wire was probably partially intact, or at least close enough to make electrical continuity for some period of time before electrical arcing damaged it to the point where it failed. So again, manufacturing defect in this component. The next example is a bicycle wheel from a road bike. So again, this was not heavily used. It's a graphite composite rim, and the client basically was riding this bike down a mountain, beach mountain, actually in western North Carolina, when all of a sudden the wheel went out of plane and scared the operator pretty badly. So
this
again,
just shows us sectioning the wheel prior to CT scanning.
Yeah, so we did destructive work on this rim prior to CT scanning it. The other thing to look at on this is that this is a front wheel, not a rear wheel where you would have additional torque on the wheel. So again, on to the next slide. So again, if you use your imagination, the out of plane area, ever so slightly, you can see like at the edge of the rim. And again, CT scans of that, you can see what appears to be delamination in the corner of the rim. So it's obvious in the center image that the sidewall of the rim has bowed out and was responsible for this rim probably hitting the brake pad on the bike. And you look at the corner on the other side, there's no apparent delamination. And again, a higher magnification image of the delamination at the right.
This shows another view slicing through the rim of the wheel along the area that delaminated here on the right image. You can see some cracking throughout the fiber composite there in the rim. I know this one's a little bit more of a difficult to visualize section, but you can see that cracking along the the area of failure there.
Well, we finished up a little early. So our conclusions here, computed tomography instruments are widely used for non-defective evaluation of components for both quality assurance and quality control and for failure analysis. CT instruments provide a volumetric examination of components. CT images will show defects present in the examined components. CT images can provide failure details that allows one to characterize defects without damaging or destroying the specimen. The data obtained from CT instruments can be used to construct 3D models of the examined component. And the CT 3D volume surface models of polymer fracture surfaces provide a better means of evaluation of the fracture surface than some of the other tools such as the stereo microscope or scanning electron microscope. So we've got plenty of time for questions.
All right, if you have any questions, please type those into the questions box and I will read those out loud. We'll just give it a minute to let everyone have time to type their questions in. Okay, what type of documentation do you need from the CT scans in order to go through a judicial process?
I guess we have yet to do that.
Yep.
So again, I think it would be a matter of the person interpreting the data being, I guess, admitted to the court as a witness.
Okay. If a defect is found, will the manufacturer pay for the CT scan and your service?
I guess that depends on what the context of the inspection is. We've done some inspections for manufacturers doing, quality checks. A lot of ours are associated with litigation. In that case, it would depend on, what the settlement detailed.
He
Yeah.
clarified or refund the client in that case.
Well, my guess would be that if it's useful information to the manufacturer, I mean, again, this is information that the manufacturer, I should think, would consider valuable if in fact it provides them with information how to improve the product. So in the case of the electrical pin, I think that allowed that manufacturer to realize that they can make their product more robust, and they had no problems whatsoever paying for this, but they can make their product more robust by using the pin in the means that it was meant to be used, or either switch to a different type of design. But again, in that case, the client had no problem whatsoever paying for that service.
Okay, did the bike wheel manufacturer compensate the owner?
No.
What is the general cost of doing a scan?
It's dependent on time. Most components, I would say you could get done for around $1,000. If you're doing more scans, or especially a large volume of scans of the same type of component, that cost could come down quite a bit. We do a lot of one-off scans, so there's a lot of, I've got to create a fixture, because if the component moves during the scan itself, the data will be ruined. So we've got to, fixture the component, perform the actual scan, and then, any analysis and reconstruction post-scan. So it's highly dependent on the volume of scans and the type of parts you've got. But for a one-off scan, usually somewhere around 1,000.
Okay, what are the hardest materials to determine a specific failure with and why?
Maybe not necessarily materials, but when you've got components that have very large differentials in how hard they are for X-rays to penetrate. So you've got like a light plastic component inside of a steel housing. Your ability to distinguish issues inside that lighter component will be extremely hampered by the amount of signal you're getting through the steel. So in general, extremely low density and extremely high density are the most difficult to do, especially extremely high density. Once you move beyond.
Yeah, especially when they're used together.
Yes, yeah. But as far as like something that's homogeneous and you don't have a bunch of different components, it would be both ends of the spectrum. But anything carbon fiber is extremely low density. We don't have any problem with that. If you wanted to do something that was paper or something, we might have some problems there. But even cloth, we can do. Extremely high density stuff like lead. You're not going to get. Pretty much everyone should know there's going to be some difficulties penetrating X-rays through lead. Your image is based on signal attenuation by the materials that you've got. So if if you're getting either too much or too little signal through that, it can be difficult.
Okay, next question. Are the CT procedures scalable to analyze municipal water and or sewer piping? Is this a typical application?
So you're talking about in the field or in the lab? So this instrument I'm not aware of any instruments that can do this in the field, although there may be something out there. But most of the times you could, if you could remove the section of interest and bring it into a laboratory, then you could image it.
Yeah, as far as I know, there's no portable CT technology that exists. Due to the relative positioning of your components is incredibly important for accuracy, right? So this thing, is down to the 10,000ths of a millimeter in terms of the, positioning of the tube and the detector and the stage. So that's not something you can move around really. Once it's set up, it's in place.
So
I think traditionally you'd end up with, portable for pipeline and stuff investigations, you'd end up with people with portable X-ray sources doing like a traditional, either digital or CR radiography.
Yep. So one of the limitations of this instrument, and again, it'll vary from instrument to instrument, is we can accommodate obviously at least a 4-foot long section and probably a diameter up to maybe 18, 24 inches.
I would say closer to 18 there.
Okay.
It depends on what, how much stuff is sticking off of your component.
Right.
So for the pipeline, if you're removing sections, certainly you can do it with CT. If you're wanting to do them in place, you're going to need to find a different method of inspection. Probably traditional radiography would work for that.
Okay. Is there additional testing required besides the CT scan that would have to be done to fully determine a cause of failure?
Usually for us, the CT is a first step. You'll CT a component, look for any internal defects, and that gives you it can also be used to memorialize that component too. You'll have what it looked like before you messed with anything, before any destructive testing was performed. So I think typically we use it in conjunction with destructive testing, though that's not always the case. Obviously, if you're doing like quality analysis, typically you wouldn't destroy that component, especially if you're doing it for something that will go back into service.
Yes. So I guess the thing is that several examples shown in the presentation. So the first example of that PVC wastewater pipe, we were able to determine that there were defects in that T prior to its installation. And that was sufficient for the client to answer their question to go back to whoever installed it. At least that's our assumption. Again, we'll provide the data. We may not know the outcome of it. In the other case of that under frequency relay, I mean, we obviously identified a defect in that magnet wire for one of the coils and had to do further disassembly and characterization to actually determine the nature of the failure. I mean, it's fairly obvious that it had like a notch in the magnet wire from the CT scans, and that might have been sufficient to determine that it was defective. But again, it'll depend on the parties involved as to the level of detail you go into for the actual failure determination.
Okay. I don't see any other questions. Do you all have any last words or thoughts to share with us?
Actually, wow, we're way under time, right? No, I guess that's about it.
Okay. Well, thank you so much for your time today. Everyone on the line, we have until 11 o'clock. So the next session starts at 11. That will be the last virtual session of the day. We will see you back here then. Danny and Ben, thank you so much for your time.
Yep, thank you.
Have a good day.
You too.